Okay, it is time to start. I see almost everybody is here. Um, you'll notice that when you join that you will be muted. If you have a question or want to raise something, then, well, first, if you look at the bottom, I assume all of you are using the Zoom app. And at the bottom is a link, is a button that says Manage Participants or View Participants. Again, mine is a little different. If you open that, you will, and click on yours. At the bottom, you should see a row of little icons, one of which is raise hand and things like yes, no, go slower, go faster, etc. So if you have a comment to make, then just raise your hand and I can unmute you to have the comment. So I hope everybody is being safe and reasonably healthy. I've been in lockdown since they announced it a couple of weeks ago, so we'll get through this somehow. Let's see there. Can you see me now? Okay, so this is moves 3302. I am recording this and it will be posted. So let's get started. What I'm going to do is I'm going to see if I can share my screen here. Yeah. It's not letting me. Okay, like I said, I'm all right. Can everybody see the slides?
Yes.
Thank you. Okay, so as I said, usually I conduct this in class, and I actually use the whiteboard quite a bit more than slides. So I've had to spend a fair amount of time kind of redoing my slides, and I'm also getting a notice that my internet connection is unreliable. Okay, so let's see. Yes, I am recording this, and this will be posted to the YouTube channel. Okay, so yeah, and as the other option is there's a chat window, you can send me a message there and it'll start blinking on me. Okay, so let's try this again. I'm going to try to share my screen. Okay, all right, so here in the first class, first I want to go over some logistics because they're going to be a little different than usual, and give a rough overview, and then just start you off on what discrete event simulation is all about. So first, logistics. As you may notice, we're in DL mode, at least to start, as long as this shelter-in-place business is in effect. The lectures will be via Zoom, as we're doing now, Monday through Thursday at 900, as we are here. It will be the same meeting. It should be the same meeting ID. So it's here in the PowerPoint. It's also in the email that you should have received, and it will be recorded and uploaded to YouTube. in some of the training, they encouraged us to use the Sakai stuff, and I personally prefer YouTube. So your mileage may vary, as they say. Now, we have a so-called lab that's scheduled on Thursday, and it may have to start with a lecture, depending on how far we get. Otherwise, basically like the labs that we had in the Java class, I'll basically be on Zoom while you work on code. See, here's the thing: is that the lectures will typically not involve programming; they will involve modeling. The programming piece will be in the labs, and we'll get to what that's about. There are going to be two types of assignments. There will be, the main ones are written, and I'm going to try electronic submission. Let's see. I apologize if I'm being told my sound is cutting in and out. My internet is spotty, unfortunately. So can you hear me now? I will just kind of do the best we can. The written assignments will not involve any programming. There will be computer assignments that involve programming, and there actually is good news on that. The news on the programming is that it will involve only really the basics of Java that was covered in the previous course. We're not going to do anything fancy. So if you have the basics down pretty well, then you're good. I will ask you to create a moves 3302 repository separate from the previous one. Since you only did that once about 3 months ago, I will post a video about how to do that again. Again, that won't come into play until we've been at least several classes down the line. Now, depending on when the quarantine is lifted, there is a midterm that's going to take place about halfway through the course. And if the quarantine is lifted, then we can just have it in class as normal. But if it's not lifted, then it'll have to be via Sakai, and I'm trying to work that out. Okay, now in terms of, before I get to this, I just want to walk you through the site a little bit. I'm having trouble finding my way here. The heck is it? Oh, drat, what the heck is going on? These applications are so user-friendly that, okay. Sharing this poll. Let's try this again. See, it's not giving me. Oh, for crying out loud. Well, I don't know if you can see this, but this is the Sakai site. I think I'm going to have to let you kind of look at that on your own. This is infuriating.
We were all able to see your screen right there.
Oh, you are? Okay, well, let's, all right, let's try this again. Okay, can you see it? Okay, so the, just at the welcome one, again, I have the meeting ID again, and everybody seems to have Zoom going on. Okay, so the syllabus is listed under the syllabus of all places, and that's fairly straightforward. One of the key things is the lessons tab. So if you go to the lessons tab, you should, oops, heck. This is infuriating. So not only is Zoom being weird, so is Sakai. Anyway, on the lessons tab, there we go. These are basically the four areas that we're going to be, actually there's a fifth one, but it didn't show up for some reason. Anyway, there will be items listed here, and then I'll have links to the slides, and then I'll also put in links to the videos. Okay, so let's go back to what we have here. Okay, so now I just want to give you an overview of, well, simulation modeling, just in general. And there are basically kind of two elements. The first of which is kind of the most important distinction to make about why you're doing simulation. And the two main purposes of simulation are training and analysis. In many of your other courses, you've seen the utility of using simulation models for training, especially some of the virtual environments or augmented environments. That's not what we're going to do here. Here we are going to be using simulation for analysis, which is to find out questions, answers to questions that we don't know before we do the model and the analysis. So the other main distinction between simulations has to do with how we model time. Modeling time in simulation is done really in three basic ways. One is time step, and if you've worked with combat simulations or agent-based simulations, you're probably familiar with that. That is not what we will do here. Here we will use a time advance mechanism called next event, and you'll be hearing a lot about this. There's a third possibility called hybrid that some modelers who have recognized the limitations of the time step approach and the advantages of the next event approach, but are unwilling to kind of let go of the time step entirely, have created hybrid models. Models like Repass Symphony is an example of this, where they try to kind of have it both ways. In fact, that really, in my view, isn't really necessary. If you understand discrete event, the next event, time event mechanism, then you don't need any type of hybrid. In other words, time step is really a subset of the next event time step. And then the final thing, and if you've had any classes over in Glasgow Hall, you've probably heard this phrase about all models are wrong. And I think that's a very important thing to remember. It doesn't mean that models are bad or unuseful. In fact, usually the corollary is that some models are useful. But it's important to understand that every model is an abstraction of reality. It is not reality itself. Okay, so I'm going to start on discrete event simulation, and to let me go back to Sakai for a second, because this is something that I forgot to talk about. There we go. In the resources section, there are the slides, there are the downloads, and so far the only download is the SimKit class library that we'll talk about in the lab. But the handouts is kind of has one important thing. This link to a PDF is discrete event simulation modeling. This is basically the text that we will be using. And it's basically a set of notes that I've written over time. So the good news is you don't have to buy anything. The bad news is, you can't get your money back. But that's where the reading and the reference will be. And if this thing kind of opens up eventually, you'll kind of see what that is about. There it is. And as you can see, it's got a bunch of stuff. And so for tomorrow, I've asked you to read just the first section that kind of talks about some of the things that I'll be getting to a little bit. If we go back to the lessons, that's where I will, if it ever comes up, that is where I will tell you what parts of it I want you to look at and what parts we'll be covering. So, so for tomorrow, I've asked you to read section 1, and I'm actually going to cover a little bit of that, but then continue with it. This first part of the class is very important to get these concepts down, because even though they're very simple, it can be very confusing in trying to deal with the models if you don't have these basics down. All right, let's go back to what we have. Okay, so what is discrete event simulation, or DES? Well, it consists of a number of different pieces, namely states, which we'll talk about, events, which we'll then discuss. There's an important construct, which is in every discrete event simulation engine, called the event list. And then I'll finish up with the basic structure of a discrete event model, and then give actually just one example, I think is all the time I'll have for today. Okay, a discrete event simulation is defined by a collection of state. And for now, we'll leave state just kind of as a intuitive, undefined type of thing. But a state trajectory must be piecewise constant. We'll talk about that in a second. And so, given that the state transitions are instantaneous in simulated time, in other words, a state variable in a discrete event simulation jumps from one value to the next in 0 simulated time. And those jumps are what we call events. So let's unpack states a little bit. So what is a state? A state is a variable, or actually a set of variables in a more complicated model, and that basically describes a snapshot of the system at any point in time. And as we look at examples, that should come into clarity a little bit more. I use the term state trajectory. Now, what is that? A state trajectory is simply can be thought of as a graph of the state over time, over simulated time. So as the simulation unfolds, if you were to look at the value of each state variable, that would form a graph, and that graph is what we call the state trajectory. Now, the discrete event states change instantaneously, and that means that the state trajectories must be piecewise constant. So what are some of the implications for that? Well, one of the main implications is that there are many, many state trajectories that are inadmissible. So here are 3 examples. So on the left, we have this exponential that we've been hearing a lot about lately. We have another parabolic state trajectory on the left in red. There is a, well, there's in blue, there's this exponential curve that we've been seeing so much about. And then the red is a parabolic curve. And then on the right, the blue squiggly one is just an arbitrary state trajectory. And these are all state trajectories, but none of them can be state trajectories for a discrete event simulation model. So these are all states that can change continuously, cannot be directly represented in a discrete event simulation. Now, that may seem overly restrictive. It turns out is not as restrictive as you might think, but we just kind of hold on to that. One of the nice things about discrete event states are that, and the state trajectories, is that they're as simple functions as you could possibly imagine. So here's an example of an admissible state trajectory. And by what is meant by piecewise constant is the fact that the state, the graph, the function is constant for a while, and then it jumps from one value to the next. And then it's at that value for a while, and then it jumps to another value, and then another, and then another, et cetera. And that's what happens. And then these jumps are what we identify as events. So in other words, at the, and actually in addition, at time 0, this very first one can be thought of as an event. And we'll see as the course unfolds what that may look like. So events are, events are what the E in discrete event simulation is. And the events are what the quote interesting occurrences. And what interesting means is that some state value has changed. That's the only interesting thing that happens in a discrete event simulation. And the thing is, in between events, nothing happens. So if we take a look here, in between what these events are going on, if this is the only state variable in our model, nothing happens between one event and the next. Now, the thing is that when you're creating one of these models, the events may schedule other events, and we'll see what that looks like as well. So basically, creating a discrete event simulation model is really very simple, although it's not always easy. The thing is that the events that schedule the other events may actually occur in an order outside of that scheduled. In other words, the events that actually occur as the simulation unfolds are not in the order that they were scheduled, but they're the order that they were scheduled to occur. Again, all of that will become a little clearer as we move on through the course. Now, how this happens is through something called the event list or future event list. I think I call it in the reading. So the idea is that it keeps the pending events in a list, or actually in a callback to what we've used in Java. You can think of it as a sorted set. In other words, if you think of events as objects, which in the implementation they will be sorted in order of their scheduled time. So the event list is basically just a sorted set that keeps the events ordered in the order in which they are scheduled to occur. The logic for advancing time now, because this is not the same as time step. In time step, time advances in constant increments. Here, the idea is that you advance time to the next scheduled event, and that could be a very small time advance, or it could be a very large time advance. And that's actually one of the advantages in terms of efficiency, because if you're in a situation where your states are not changing that much, then in a time step model, you would basically be sort of polling and checking every discrete event, a discrete amount of time, whereas in a next event in a discrete event model, you basically skip over all that uninteresting stuff, that is things where the states are not changing, and then you move to the next event. And sometimes that can create very large advances in time when not much interesting is happening. So the event list, in addition to this sorted set, processes the event by advancing time to the next scheduled event. It removes the event and then processes that event. And that event, remember, is going to be defined by a state transition function. We'll see examples of this. And you just keep going on that until the event list empties out. That is, at some point, the event list will have nothing more to do, in which case the simulation universe dies, if you can think of it that way. And sometimes we will artificially empty out the event list, which will be mostly what we'll be doing in the beginning. That is, we'll say we're going to execute it for this much simulated time, and at that simulated time, there's actually kind of a destruction event, a universal destruction event that cancels and removes all the future events and basically blows up the universe. But we'll get to that in a second. Okay, so now if you think about that, and you think about what a sorted set is, if you were to instantiate a sorted set, it would be initially empty. And so the algorithm, the logic says, okay, as long as the event list is not empty, then we'll keep processing, but initially it's going to be empty. So you got to kickstart it in some way. In other words, you need at least one initial event. And that initial event is what we call run. There's kind of a historical reason for run, but that's just what it's called. You can think of it like the main method for, if you remember in Java, where does Java know where to start? Well, it starts in the main method for the class that you pointed to. Similar, the run event is always scheduled to occur at time 0. So we always put a run event on the event list so that in the beginning, there's always at least one event to process, and it occurs at time 0. And other than that, it's processed like any other event. And what the run event does is up to what the modeler defines. So we'll see what that looks like. So here's how we define a discrete event simulation model. There are 4 pieces to it. The first are a set of parameters, which are variables which do not change during a single simulation run. The second are these state variables that we've discussed, and these are the ones that typically will change during a single run. Sometimes by chance it may not change, but typically we've defined state variables because they will be changing. If you have a variable that could never change, then it's not a state variable, it's a parameter. The events are when the state transitions occur, as we've discussed. And the scheduling relationships, and this is kind of the important thing, is that these are the relationships between the events that schedule the other events. So here's our sort of hello world, if you will, example, and that's an arrival what I call an arrival process. If you've had stochastic processes, you've maybe learned about a Poisson process. If you haven't, then don't worry. So the idea is that there's going to be a sequence of times. So the parameter is this sequence of times that are going to be between the arrivals. So you can think of like arrivals of customers to, say, a bank, or customers to some facility, or just the arrival of any kind of thing to some system. Exactly what it is kind of left undefined. So in our we have one state, which is going to be the number of arrivals. We'll call it n. And so that's the value that's going to change. And all it's going to do is just count the number of arrivals that we have. So the run event, we're going to have 2 events. So there's always a run event. And the run event is the responsibility of the run event is twofold. First is to initialize all of the state variables. So here our first state, our only state variable is n, the number of arrivals. And so the run event will set n equal to 0, which is the initial value of the state. And it will schedule the first arrival with a delay of the first t sub a value. So t sub a, or that is that sequence. So the first value is going to be used to schedule that first arrival. The second event, we'll call it arrival. What we call it doesn't really matter. But every time there's an arrival, the state that's counting the number of arrivals is just going to increase by 1. So our state transition is to take the state value n and increase it by 1. I mean, it's about as simple as you can get. Where are we? Yeah, so now each arrival is just going to schedule the next arrival with a delay of the subsequent t sub a values. So what does that possibly look like? It will look like something like this. So here's a possible state trajectory. So at time 0, the value of n is 0. At the first value of t sub a, time later, this is the first arrival event. And it changes the value of n from 0 to 1. And then the next t sub a value is this. And it will change the value of n from 1 to 2. And then the third value of t sub a is this. And when that occurs, it will change the value from 2 to 3. And then it just continues. Any further state trajectories are going to be off to the right. So this is a state trajectory that will be produced, or a possible state trajectory that will be produced by this model right here. Okay. Let's choose my virtual. Okay, let me. Okay, so that nearly brings us to the close of this, and let's see. I think I unmuted her. It says unmute all, and I think I've unmuted you, but no, it says I haven't. Anyway, so any questions? So for tomorrow, read the first section. It goes over some of what I've talked about, and we're going to delve a little bit more deeply into how it works and go through a simulation by hand. So if there are any questions, you can unmute yourself. I tried to unmute you, but it didn't seem to work. As I said, I am recording this. I'll try to piece together a recording that makes some sort of sense on this, and we'll see you tomorrow if there's no other questions or concerns. I will stay on the line for a bit. Okay, I'm seeing some no's. Okay, everybody good?
Good. Thank you, sir.
Okay, we'll get through this somehow. Thank you, and thank you for your indulgence and with the internet problems that I've been having here. Hopefully I can get them figured out. So again, I will stay on here. You can leave, and I don't know if you have a class next, but I guess the time between classes is a little bit easier to navigate. And I will see you then.